all his suspenders?
I was a one-night stand, and I made my head into a lampshade, and I had a desk with a
With a what?
I was a desk.
Oh! How is that a one-night stand?
Singular nightstand.
One night stand.
That's funny because I just went to jail to a church party.
What did I hear?
But I don't call my nightstand a one night stand.
Yeah.
I only have one nightstand.
That sentence starts so bad.
You should have two.
So innocent. Definitely have two.
That's everybody has, right? Two nightstands. All right. Let's get back to the topic. So, where we are and where we are heading to, I'm a bit lost.
Random walk? No, we're not.
We're past that, right?
We learned how to put random walks into MATLAB. In MATLAB today, I was
Lori Huggins.
No, I'm lost. What did you say?
You say it.
We learned how to do a random walk in MATLAB.
Oh.
Picture it on a 3D graph.
Nice. It's a 2D or 3D?
3D.
3D.
All right. So you guys now get a picture of how it's a Gaussian distribution front center, right?
It's taking this long.
Yeah? Good. Good. So we have passed the random walk phase. Everybody is conscious it's not a drunken guy can do random work now. We have moved over that teenager phase. Now we're getting into a solution phase. So in the past 2-3 lectures, we introduced the Flory-Huggins theory. We talked about while you're mixing two things, what's going to happen in the entropy and the enthalpy. Now, today, let's continue the journey. But we're going to get into the realms about phase diagram. And we specifically will cover two things in a phase diagram. And it is about when does you have a binodal distribution, and then when you will have spinodal decomposition happening. So let me first introduce the concept to you guys, then we will go from where we left it from last time. So a phase diagram, it's not an x or y axis, okay? So again, it's a diagram, or it's a schematic picture shows you what's going to happen to your material. It's a box, and in here, it's a composition difference. So, which is, again, we're going to mix A and B, all right? You're going to have A plus B, then we can plot a percentage of A. So this axis is percentage of A, from 0 to 100%. Or we can remove this just to say this is going to be 1. So 0 means most of them are B component, and 1 means it's almost everything is A. And this is a temperature. While we plot it against the temperature, I'll give you a general case what this would look like. This is just a theory of what could be a most ideal case in terms of phase diagram. I didn't break anything, huh? And there is a curve in of that. I use the dashed line. It's a little bit narrower. And this particular curve, it has different name. So this called a binodal. This particular one could be spinodal. And we will learn that if you have a mixture sitting in different area, it will do differently, okay? So we can just say, arbitrarily give an example that in the top of this diagram, there's going to be a one phase, which means every going to mix, and in the bottom, it's going to be a two phase item. So if you have this curve, it's quite useful if you consider mixing or compounding or preparing your polymer solution or trying to make a binary blend system, right? So today we're going to talk about two specific things. First is what is the Binodal, what is the concept of this curve, and why it's called this way along this curve. Second is what is Spinodal curve, and how do we get this curve, and what does this curve mean for a polymer blend system. And these three phases actually correspond again and again. I'm going to mention the eraser and how does it respond to. So in this phase, it's pretty stable, which means if you have a thermal fluctuation or if you have a local concentration difference, it's going to come back to the original state. So it will not propagate, and everything will still stay in one phase. So this, if you don't give any perturbation, is still stable. So that's why we call it metastable. Between the spinodal and binodal, in this tiny region, which I will highlight, half of it uses dashed slash line. Those are metastable area. Metastable means it's kind of stable, but it's super stable. So you can think about this. This is a patient needs some treatment for their mental. So when they take medicine, it's kind of stable. But if it's forgotten, it's gonna decompose. And if you do any small perturbation, it's fine. But if you create something called a nuclei, or if you initiate a nucleation process, you're going to quickly go down to have two-phase system. Well, nucleation going to happen because the system will go down to the lowest energy state. So two-phase, this is basically unstable cases. In anything in between this region, it will phase separated into two-phase. No matter what you're going to do with it, it's just not going to be stable. So if you think about what happens in these three phases in terms of free energy perspective, you will start to understand why we have those kind of three different regions. Okay? And the key to understand this curve is we need to understand what's the definition of this curve and what's the definition of spinodal, what's the definition of binodal curve. Then we can plot this out. And there's one more interesting point on this curve is you can call a critical temperature that at which, or above which, in this case, it's always going to be one phase. So this is going to be defined as critical temperature, or the highest point, where above this critical temperature, it doesn't care how much A you put into B, it's always going to be mixed phase. Okay, so this is a highly diluted, a highly concentrated topic for today's class about the phase diagram, and we will go back to Flory-Hagen series to see how we can understand and use the Flory-Hagen series to derive what's going on here. So anyone can help me for the Flory-Hagen series? How can we compute the entropy or enthalpy contribution? All right, and that's entropy contribution if you just mix a binary thing, right? And we know the enthalpy is equals to enthalpy divided by RT is equal to phi 1, phi 2, chi. That's some of the background information for us to move forward to understand what's going on here. So let me first introduce the idea of what is Binodal. So number one is what's Binodal and how do we understand that? So which is this, let me use a different color so I can highlight. So the binodal gonna be this. So this color is binodal. Bi means there's two things. There's two instead of single, right? Bi is two. So binodal means there's two faces that happily live together and they like each other. Okay? So definition is if you have mixed A and B with a certain hypothetical concentration, okay, we can just give a random number, say we're going to put a x1 concentration there to start off at this temperature. Then you can kind of understand if your material will be in this phase or this phase or this phase. So on this curve, specifically on this binodal curve, which means they can be phase separated into two things and they're happy. To be more specific, I mean x1% of A in 1 minus x1% of B is the mixture we start off, right? We have x1. Sorry, it should be the B, right? By definition, so this is percentage of A. In this case, if it's x1, that means there's x1% of B, correct? Everyone? Oh, doesn't sound good. It's so quiet, all right? So is there other way we can describe it more clearly or better for you guys to understand? We can use some example. I think daily life everyone can see is maybe think about milk. Milk is an example where you have fat inside of water. While they sell you the milk, if it's directly out of the farm, if it's in good condition, it should be relatively homogeneous blend in terms of A to B. Okay, so you can think about a hypothetical case where you have 10% of fat in 90% of water. So binodal means on this curve, your material can be phase separated into two phases, and they are happy. And anything between these two, they're okay. Specifically, what does this mean? It can be separated into 2% of fat in 98% of, it's just a random example, okay? And you can also have, in another case, where you have 18%, because you still need to consider conservation of mass. There are going to be no fat loss, but you can now have two phases exist. So if you still think about, you have your cup in the morning, you're going to have your milk here, right? So in this case, what does this mean is in the cup, some region, it's going to be more fat. So let's call it 18 region, and some region going to be 2%, and they're just going to be intermixing with each other. Totally phase separate means you're going to be only so total phase separate means you're going to have always top is 100% of fat, which compose the volume of about 10% volume, right? And bottom is majority of water. This happens if you don't drink the milk for months. It will not only phase separate, but also smells really bad.
So that's not bimodal if it phase separates.
Yeah, no,
So
that's the unstable phase.
Two miscible components.
Right. Two miscible components, but they are slightly different in concentration. Yeah, so In other words, you're going to form two faces, but each of them has a little bit in A to B. Still, this is a mixed face, right? This is still another mixed face. This is happening in many cases called binodal, which means you will have two components in the system, and none of them are purely A or B. Okay, that's what I mean by here. Some of region are 2%, some of region are 18%, and they're just uniformly distributed, but they are two faces. It's called a binodal. So, if you think about what kind of reason and possible ways you can reach here, that means the energy potential for the fat, for example, in this particular case, has a similar chemical potential in the 18% of phase versus 2% of phase, right? So there's going to be no driving force for them to further separate. It's going to be, this means chemical potential all the way, how we write it. So mu fat in 2% going to be equals to in 18%. So if they're equal in chemical potential, then there's no driving force for them. One goes to the other, or vice versa. Okay? I want to take a step back and let you guys think about what we just talked about in this binodal phase. Rebecca? Yeah?
So you say if the mu's are equal, that means it's an even distribution?
It means they will not have any driving force for them to further separate or further mix. It's like a stable system for, it's pretty happy for like this component A, or we know it's a fat component. Okay. Otherwise, it will like to phase separate more into two systems.
In a system like that, does that mean that your free energy is at a minimum?
Very good point. I'll get to it just in a moment to continue and talk about that. Okay? So in some of the last lecture, we talked about how we can use chemical potentials to see if your material will be mixed or demixed. So we discussed a chemical potential map versus different component, which is drawn in this way. It's gonna, on the horizontal axis, it's still gonna be A, gonna be 0 to 1. This is gonna be x1, or how much percentage you're at. Okay, so 0 means it's pure B, 1 means pure A, and somewhere in the middle you can see it's half A. It's right here. So in this curve, we plot delta G, or the free energy for the system. And we talked about several cases where I want to get back to with the interesting or special case where we're going to draw. Okay, so this is random enough for you guys to see what is delta G at different composition, okay, versus A. So what this curve will tell us, or this particular curve will tell us, is you can use it to understand if your material going to be phase separate or not phase separate. We defined a scenario that if you take the second derivative of delta G versus x1, or component of the first, so you take delta G twice, the x1, if it's larger than 0, this is a bit complicated mathematics here. So that means second derivative. I need help. What does this mean, second derivative? let's give a,
Ultimate maximum.
yeah. So let's try a few examples. How about, this is now a random equation. What if we do second derivative of y to x squared? Anyone can help me with the math? 2. Oh, very good job, right? So this will be, if you take a first derivative of y derived by x, will be equals to, this is going to be 2x, plus this is going to be derivative of x will be 3, right? And last component will be 0. If you take another derivative, you will reach here. So that means this particular function is equals to 2. Take a second derivative, which means it's bigger than 0. So if you plot y, x, it's going to be a curve, look like a, let me make sure. If it equals to 0, going to be 1. If it's going to x equals to 1, going to be 1 plus 3 plus 1 is going to be 5. Okay, so it's going to be look like this. And this is going to be minus 2/3, which means if its second derivative is 2, your curve will concave up, right? So that means the system is stable, is locally stable, or if you have a system fit this condition, it will not phase separate. It will be sort of one phase. Because we talked about that, let's talk an example. Y stable for let's use the delta g, delta phi x1. Why this is stable? And this is one of the important questions. If we take a second derivative of the g, or free energy, to the component, if it's larger than 0, which means your curve is has an opening angle towards up, it will be stable locally. And why is that? And we talked about a little bit last lecture, so let's revisit what this means. I again want to use this curve, okay? So we can plot the g versus if it's follow this way, right? That's the case where second derivative is larger than 0. And we will spend a minute talk about this and talk about second case. When case 2, when delta g, second derivative of x1 will be smaller than 0, then this is an unstable system. So again, let's use this example. 10% of fat and 90% of water. So what we can do to see if it will phase separate. So let's assume it will phase separate. That means somehow if you move a little bit of fat into the water in a very tiny location where to the center you got 11% in 89% of water locally. And by conservation of the mass, you cannot pull fat from nowhere or lose fat from nowhere. That would be a dream for someone who wants to lose weight, right? Or for me, I want to gain some weight. It just doesn't happen, right? It has to come somewhere. So this 1% will give to the local the other one, this which is 99% of fat and 91% of water. So which you think about this case, a glass again. So which means in here, I'm going to split this one into two parts. One is a little bit more fat, the other is a little bit less fat. If you recombine them, it's the same amount of material. You don't lose or you don't gain anything. So then the question is, will delta G, will G for energy, free energy, before is smaller or larger than after. So what does this mean? So which means before we know it's 10% of the fat, and after we know it's 9% and plus 11%. So how does these compare? If this has low energy, it has no interest to move on to the high energy state after they split it into two parts, right? If you add these two together, if it's higher energy than that, then it seems like you're hiking up in the energy map, energy landscape. You don't want to hike up in the mountain. They want to go down, or they want to lie down to go to the energy lower state. So in the other case, if the delta G before is smaller than this, which means no, not going to happen. So this process will not going to happen, right? Because you are gaining free energy if they're going to phase separate into two cases. So this is not going to happen if that's the case. However, if you have 10% of fat has larger free energy before they separate into two pieces, then it's going to happen, and it will be more than happy to go there. I won't separate myself into two pieces, right? So how do we know if this is going to be bigger or smaller? How do we know if 10% of fat will be smaller than the combination of the other two? Please, someone help me. How do you know the free energy of 10% will be smaller than a linear combination? So if you split these two, you're going to have half of this and half of that, right? You're going to split it into two. And how do you know these combined will be bigger or smaller than that? Huh?
Just look and see if it's bigger or smaller. I don't know.
So the trick is here. In this particular plot, where you want to see your neighbor combined if it will be higher energy or lower energy than yourself. So if I'm sitting here, which is 10% of fat, which maybe I'm a little bit smaller than that. So I split into two, right? 9 and 11%. Let's zoom in this part. So if I zoom in, so this will be local region like this way, right? So I got how much? 10% of fat. This will be free energy of 9%. This will be the free energy of 11%. Correct? Everybody got it? And this is delta G. This is a G. And this is the volume fraction. So can someone help me now? I already gave you a hint. Hint is here. And I have drawn this curve.
Spontaneously go from 9% to 10%.
So in this case, will it spontaneously happen? It will go to these two. Will I cut myself into two pieces and become in two parts? 1/3. We need a vote. How about we have that? How many of you think it will not happen? Raise your hand. 1, 2, 3, 4, 5, 6, 7. Okay, Michael, you're the last one. Why you are so slow? I think you are following the other.
Is that showing the energy is decreasing if you split into?
So that's the question. If that's the key question. If the energy is small and larger before and after the split, is a key reason will it phase separate or not?
Is it splitting at all?
Oh.
Yes. So in other words, I already gave you some of the more hints. So let's do this. So how about the energy before we split? Let me use a color. So delta G will be this one, right? If it split it, you're going to have 2 here and here. But you got equal part of 2. So you need to add the 2 of the energy and divide by 2. Right? That's the total free energy. So it's basically draw a straight line and take a center piece of that. So which one is high energy, before or after you split them?
After you split, it's higher energy.
Will it split then?
It would split then? No.
You know, I was asking, will it split?
I think it
Then it don't want to split, right? Because after you split, your energy goes up, free energy. So does it make sense to you guys now? If the energy diagram looks like this, it will choose not to split. Just because we did a scenario, if they split up into different composition, a linear combination will not fall up. And it's the true, no matter if you split this way or if you try to split in, I'll give you another example, okay? If you try to split 10% or 15%, that's another possibility, right? You still, if you add 2, it's still going to be the same here. If you pick 1, 5 here, 15 here, if you draw a line, it's still going to be taller than before you split. So in other words, that's a definition if you're going to have a system where it chooses to phase separate. If you take a second derivative of g derived by composition of x1, if it's larger than 0, it's happy where it is. It don't want to go anywhere. Case 2, how about in this case, if we take a second derivative, if it's smaller than 0, what you're going to have is now a curve look like this. It's going to concave down, just because second derivative will tell you what's the sign in front of this, right? So I can give you an example what this would be like. So you can think about y equals to minus x squared plus 3. If this is a minus sign, that means it will concave down both ways. And now let's do the same tricks again. In this delta G, we call it will it split or not split. We again going to take a 10% point.
Yeah. Bye.
It's gonna, right? Because then 10, we can do 9% and 11%. And if you split half-half, after you, this is bad, bad line. Let's do a bit better one. If they split it, and then you combine the energy, your system lose a little bit delta G. Right? It will try to split and phase separate. So we covered this part is about where the system has been locally stable. So definition is if you take delta G, took a second derivative in the volume fraction of x1, then look at a sign. So in other words, if it's delta G show a curve, empty opening showing facing up or facing down will show different property. What if you have more complicated? What if your G versus X?
It doesn't fail.
Huh?
Said the line doesn't fail. You can still draw a line between them, right?
Yes, if you take a second derivative, you still be able to find when they will be mix of wind and wave. So you will have local regions. So this is facing down, this is facing up. So depending on the fraction, you will have different cases. Similar to here, this funky curve I draw you, it shows locally in the center of here, you would have unstable state, right? So in other words, if we take second derivative, which means this point, you're going to reach 2 points on this curve, A and B. So between A and B, your second derivative is negative, which shows your system will choose to split into multiple components if you are somehow within the region of volume fraction of A is A%, B is B%. It's just some number in between. But if you're outside these, they are perfect happy, so it wouldn't do anything. Okay. Let's move on to talk about how about this Binodal case. Binodal is a very special case where your system is, no matter if it will split or not, it just will be happy there, and no matter how much percentage there. Okay. So in other words, they're going to be 18 or 2, or it's going to be somewhere is 17 and 3. They were just happy. They don't choose to phase separate. They're just happily there. So the definition of this is where for the component has similar chemical potential in one phase than the other. I'll just show you guys what this means in the next half of the class. Okay, we can take a short break. Then we can come back to talk about this Binodal phase. Five minutes break. Wow, I think the weather really affects everyone.
Yeah, low energy day.
Seasonal depression is real.
The weekend looks like nice.
Yeah,
Gonna be good
nice.
weather.
That will be nice.
Mm-hmm.
It usually never. I feel like it's very rare in the south for it to rain all day.
It is usually just a thunderstorm, right?
Usually it's just like a quick thunderstorm and then it stops.
Right.
I feel like I'm back in Indiana. It just rain all day. I hated that. But I do like how there's no thunder and lightning today. I'm not a big lightning. I do not like thunder and lightning.
Right. Okay. Good.
Do you have any fun plans for the weekend?
We had some. We was hoping to pick a weekend to go to New Orleans to show the kids the Zoom there.
Oh.
We get the season pass, but in the summer it's so hot that animal was like lying down. They don't want to get out.
Yeah.
This is the perfect time.
That'll be fun.
Yeah.
gonna have to like find some needles upstairs and inject caffeine into my veins. Yeah, what are you doing with those needles? Don't worry about it. That'd probably be on the next episode of like Spinodal Point stuff.
Oh my god, did you hear about it? There's a biometer, interesting old creation. She didn't do it right in mud, and her whole face caught on fire, and she died.
Here?
No. The biometer.
Those biometers. Dummies. Squeaker. Juice.
Yeah.
I hate that noise. Not a pair, but there you go. Got worn out.
Yeah. The soles are not great.
Sit back.
Yeah.
And you can tell me that I should still work out before I have a session.
Yeah.
Show.
Work out after. Oh no. That's bedtime.
Deal with everything else.
That's a good idea.
Yeah, we do a workout hot tub after school, and it's like a nap. That's what my grandpa does. It's all day.
Why do you even do that? I love everything you say. Sugar just kidding.
Most of it is me quoting my grandpa.
I want to meet your grandpa.
Mhm.
You guys would appreciate
Oh, do I need to look?
Okay, everyone.
It's time for pause. Answering my
Let's finish the second half. Okay, so we discussed how you can find the Spinodal point. Well, basically, within those points, your system will not be stable. Okay, so if you look at here, so that's basically saying this. We found the solution to draw this one, this curve. This is a Spinodal curve. Okay, so for Spinodal. So that's the boundary between stable and unstable. If you're within this curve, you're not going to be stable, okay? Spinodal basically point. Spinodal point is defined by delta g squared derivative of x1 Spinodal point, okay? So in other words, these 2 points are going to be the Spinodal points. So example are A and B, point A and B. Does it make sense, everyone? So if we're within the point A and B, it's going to be phase separate from 2 phases. But if it's outside these 2 points, now every data point on here, 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 going to be stable. Saying on this side, if it's above B, it's going to be stable. So only concentration in between XA and XB going to be not stable. And how do we connect with this curve? How do we connect this curve to that curve?
The integrals and derivatives.
Say that again.
Never mind.
Yeah?
The
Chris?
equation.
I don't know.
So it's actually fairly easy. I'll show you. So this one plot is temperature versus a volume fraction of A. In this way, we plot the G versus volume fraction. So what the difference is the temperature, right? So basically, this is under one temperature condition, under one temperature condition, 1T condition. So you can think about as a special case where you do one temperature, you take a cut here, that will be related to this curve. It's a little bit long because no, it basically you only get 2 data points in Spinodal. Spinodal point at this particular temperature. Let's call it temperature. How do you guys want to call it?
T1.
All right, let's call it T1 because it is T1. At this temperature T1, you determine the data point of this one and data point of this one, right? That defines when the spinodal point is going to happen, okay? So if I'm the one doing from scratch, I'm going to plot this curve. What is going to happen is I'm going to have 0 to 1 volume fraction of x. They're going to be the temperature. So I only calculated once at T1, right? So which means this x is going to be T1, right? Like Michael says, it's a T1. And I determined basically 2 data points. At temperature T1, I take free energy, I take second derivative. When second derivative equals to 0, it's a spinodal point. So if you do the math correctly, this is example point A and B here. So you're going to get x volume fraction A and volume fraction B. So you can plot it out now, come back. You can say this is going to be volume fraction of xa, this is going to be xb, right? So you can put it here. And in the middle, in here it's not stable, right? And here it's one phase. In the center it's not, it's going to be 2 phase. Okay, so you basically get these 2 points. Okay, now if you do a second point, Michael, how do you want to name it now?
I'm going to go with T2.
Okay, let's do T2. You want T2 higher or lower than T1?
Let's go higher.
Okay, T2 going to be higher. So at T2, because delta G will be different, right? Delta G is equals to delta H minus Ts, delta S. So effectively, this curve at T2, you now have a slightly different curve, look like this. So T2 will be, somehow maybe just to have a little bit difference at T2. Again, you're going to take a second derivative. You can find 2 data points. A prime, volume fraction B double prime at second derivative of G equals to 0. So that's a new spinodal point at temperature 2, right? Michael?
Yes.
At different temperature, your delta G will be different. And for each delta G curve, you will get 2 new spinodal points. Okay, we did T2. How about Nathan? How about T3? How do you want T3 look like?
Lower.
All right, so we're going to have T3. We just talk about T2, we're going to have 2 new data points. So we're going to x2 double prime, xb double prime. Let's assume they're here. Of course, they're going to be at the same temperature. We're just going to do one more data point. You will find 2 new curves that are called xa prime, xb prime as a new spinodal point at temperature T3. Well, we don't need to go through for all the classmates, but I could ask everyone in temperature. But now you connect the dots for the different temperature. You will see That's this phase diagram. This is how you get the spinodal curve. Everyone clear? So this is how you can get a spinodal phase diagram. The trick is you're going to first understand what happens at one temperature, which is this section, which is T1, to understand what's going on here. And we need to understand when does it don't want to mix, when does it want to mix. So that is defined by this parameter. If free energy takes second derivative is larger than 1, or if this goes up, it will be stable. If it's -1, it will not be stable, which is in the median region. And spinodal point is just the transition point when it's going to be just coming from stable to non-stable state. So which is it's just a transition when second derivative will be equal to 0. Okay?
What happens if it's like only like 1 point instead of 2? Like that kind of looks like it's got, I guess I thought it's like a bimodal curve, I guess. But what if it just has 1 like minima?
Okay, very good call. So what if at a very interesting temperature, they only have one, looks like G, x, volume fraction of x from 0 to 1. So you're only going to have one data point, which means there's going to be exactly this point. Okay? Or above this, everything will be start to mixing. It doesn't matter. So in other words, if you continue to go, you're going to be in this one phase. Throughout this range, there's always going to be mixed. Okay? So everyone clear about spinodal, which is the boundary between mix or not mix. And the key is we just need to look at what is delta G, take second derivative, see, then we did actually again together for look at if the milk is phase separated into two different volume fraction. From 10% to 9 to 11, we're the mix, right? We did that. Okay, so what about this blue curve now? We did the green one. If we solve the blue curve, we actually finished the chapter 7. And how do you solve the blue curve? Oh. So what's the definition of blue curve? First, let's talk about what's the definition of blue curve.
It's where they're separated but happy, or
No, it's like it can be phase separation, but it can be any volume fraction. In the, I think Binodal is kind of a bit hard to explain. It's basically say you can be any volume fraction or phase separation between them. They're kind of mixed state, but they're not fully mixed. I still didn't think I explained clear, but let's try to figure that out. What's going on for that?
So mathematically, is that the first derivative equal to 0?
Not that simple. It's more complicated than that. It basically says if you have any phase separation along your line, it's gonna be the same energy before and after the phase separate. It's not gonna be up or down. In this case, we basically, in one case, we talk about, for example, if we phase separate from A to B, right? So this would be a bad. So this is going to be the before. It's going to be G, X. And this is going to be the after point. Right. We talk about the case where either this after will be higher or taller, right? If it's higher after you phase separate, it will not phase separate. If it will be lower after you phase separate, it will happy to phase separate. then there's a very special cases. What if before and after are equal? If let's say before and after are equal, which I cannot show in this particular curve because it will not happen in this kind of curve shape. So yeah, so basically what does that mean is before and after, either way it will be happy. It doesn't care if you phase separate or not, right? In this case, because delta G is 0 before and after. So
equilibrium thing if that's the case? So like equilibrium type thing if that's the case, where it'll go?
So that's why we call it metastable. So if you somehow created a nucleation, then you can drive the system to fully phase separate. Nucleation is just a nuclei, and then you have pure A start to grow.
And you said phase separate if it's got a higher free energy or lower free energy than theory?
It's lower. After you mix, if you are here, then they're going to be spontaneously reduced energy, right? So which we just showed here. So we won't go through too much mathematics, but effectively, what's binodal curve is actually the intersect of two lowest data point here and here. So the binodal point is the point it's a contingent from the minimum data point in A. We can call it, how do you want to call it? Let's call it C and D. It will be easy. So that's going to be XC and XD are the binodal point. And why? This is these two are the binodal point.
Is it on like?
So just why they're the binodal point?
Yeah.
They're on like the boundary between like metastable and stable, kind of.
Yeah. That's one of the interesting definition. Yes. Any more thoughts? Why C and D are called binodal point? If it's tangent, which is the tangent of these 2 points. So if in other words, C always going to be smaller than A, D going to be slightly bigger than B. So if you plot here at this particular energy, or this particular temperature T1, you will have 2 new data points, which are a little bit further apart than here. And these two are going to be your binodal point. Michael?
Would you solve for those points by finding like the first derivative, seeing where the first derivative is equal to 0, and then figuring out that's a local minimum or maximum? And if it's local minima, then that would be the binodal point?
But it's not that simple. It's actually talks about the free energy of before and after.
Okay.
So what the definition of this is, let me make sure I got this correct. So before, we can use this as a free energy for one component. So mu1 means chemical potential. Okay, let me write it down. Chemical potential is chemical potential. So this is, you can think about the energy, free energy for the one component. The delta G is a combination of all the chemical potential in your material. This means, that's fine. Before and after you have phase separation, it will be the same, chemical potential. So this will be the before, this will be the after you have any binodal or phase separation. So binodal point is basically, say, if you jump to here, this will be the same, chemical potential for the one. You also need to consider the B component, because in this here, I still want to go back to my favorite model where we have 10% of fat milk. So which means in one system, you now have two material, right? 10% of fat and 90% of milk. Oh, no, water, not 90% of milk. So chemical potential for fat and water are going to be slightly different. But if you had to form the binodal phase, which means before and after binodal phase, the chemical potential for the fat would be the same as for the water. It's a little bit tongue twisting, but let me show you what this the other. If we write down the other component, so we can also write down other component after we. You can think about this as the chemical component for fat, this is chemical component for water, and x1 and x1 prime are just the two data point on your curve. So effectively, if we look back, we can basically hence are going to replicate that curve, but with a little bit simpler term. So I'm going to draw it more clearly. This is going to be volume fraction C, volume fraction D. In other words, this defines as C will be equals to D at two data point. So they have similar chemical composition, chemical potential for the fat, and there's the second component will be the same. So using this definition, you can already get the slope of this and intercept on the 0%, right? So you can, this is basically 1, this will be the 0, so you can get the slope. So the delta G for the system is equals to delta Gm will be chemical composition of first component will be Xc plus N2 Xd. So that's the total free energy. It's a linear combination of two parts. And you can basically get delta G, and you can write as composition of C delta mu1 plus 1 minus X mu2. And this you can basically write as y equals to, and this is slope K. This will be the intercept. This will be the intercept B. Okay, because this basically is a linear function for these binodal curve. I think this is a little bit harder to understand with the binodal, right? Any question? I want to take a pause and make sure.
So, what part of this whole process gives you the 2 points on the binodal curve for the over the entire temperature range?
So, while you shift the temperature, this curve will be different. So let's say this is temperature T1. Yeah. If you get a T2, this maybe look like this. For T2, then you will have 2 new data points, right? These two values are going to be different. So in the T2, you're going to add 2 new data points, which is roughly here and here.
But
so
you get the data point. How do you get the specific points?
We will do that in the next class. So because we know what is delta G, right? Delta G. So all these didn't to talk about the details, but delta G will equal to phi 1, phi log phi 1 plus phi 2, log phi 2 plus phi 1 phi 2x, or chi. Or basically, you can also write phi 1 basically is a volume fraction of one component. So I used it interchangeably, but this is basically the x1. Ln x1 plus 1 minus x1 and ln 1 minus x1, right? Phi 2 is basically the second component plus, and chi is a no. So basically G is a fancy, complicated equation you need to solve to plot it as out. So if you have a computer, I'm now going to erase here to give me some room. So if you have very powerful computer, you can see, you can define this is basically y. It's y-axis, which is delta G, and these are the x-axis, right? The only change parameter is x1. All the rest are constant, but it's not a simple equation y equals to linear, no, something like that. But if you plot it out, use a computer, for each x1 from 0 to 1, you will get a delta G, and this would be the curve you're going to get. And this is temperature dependent, because x has a temperature turn into that. Or the chi parameter in this case.
Chi parameter has a temperature?
Yeah, so we do.
Relying on temperature.
Delta G will also depend on temperature.
Just because of chi, though.
Yeah. Well, basically chi and delta. So these two parameters, they have different dependence on temperature. So that's why at different temperature, your delta G curve will be different. So let me show you. So what if we draw a delta G versus the x1 at different temperature? So we can give, again, T1, T2, T3. I like the example that Michael helped me. So let's reconstruct this one, which means T2 has a little bit wider spinodal point, right? T1, so let's say this is going to be the T1 in delta G, where you have two spinodal points. So while you change the temperature, because your G function depends on the temperature, so you're going to have, we call it T1. So the T2 is a little bit higher. At the second temperature, this is a little bit hyper-theoretical, but give you the example. If you have different temperature, your delta G will show a different curve. It will shift around. And this might be the last T equals to T3, where you now start to have, T3 we said is lower temperature. Yeah, that's correct. So if you connect all of them together, that's your spinodal curve at different temperature.
I got kind of a conceptual question. So
yeah,
I haven't really been thinking of free energy as like change in G. So, but it is. It's the change in G from what to what. So like over a temperature range. But what are we? So if we're saying that delta G, it's the change in free energy from assuming kind of one temperature or one composition to the next. What, like, so I get it if you'd say delta G T2, but what are you comparing that to? How do you
how do we compare these three?
I'm just thinking. I'm just trying to understand free energy, the delta G term.
So what is the?
Yeah, so it's just the change in free
so
energy.
No, sorry. This should be G, not delta G. Not the delta G. My bad. And this should be the G.
Okay.
No, typo.
What about that graph too?
Yeah, that's also G. The delta G means before and after, so that would be the delta G.
Okay.
Good catch. I'll give you a bonus point. Okay, so that's relatively clear what does spinodal and binodal means for the phase diagram, and how we can use Flory-Hagen theory. We haven't used much, but in the next class we will discuss more how you can, if you know this, without knowing anything else, you can basically type in the computer to generate this curve, then this curve.
So the only two parameters we've talked about with G is temperature and composition.
Yeah.
What about like pressure?
So in this case, we just assume the pressure is the same as a constant. Of course, pressure will also slightly influence the shape of this. But most of the time, it's a different problem, more prominent in the gas phase. In the liquid phase, pressure is not that most important, most the superstar, most the shiny thing you want to pay attention to.
Right.
More questions?
Kind of another
Yeah.
conceptual one.
Yeah, please.
So what is it about those two minima that represent like the transition from your stable to metastable?
So you talk about this
Yeah,
binodal
why is it
point?
those points that represent like when you take them all at all these different temperatures that represent the difference in between the stable phase and the metastable phase. Like why is that the barrier between them?
Why this is in the metastable phase, right?
Like
It-
why? So we get all of the
Mhm.
we get all of the points at the different temperatures for the bimodal part.
Right.
And then when you draw the curve on the like temperature dependent
Mhm.
diagram over there,
Yeah.
that creates that curve that separates the stable region and the metastable region.
You talking about this one or this one?
The far left one.
Okay. So
So that blue
why?
line-
Yeah. So you basically understand between two phase and one phase, right? It's pretty clear for you. When does it two phase and one phase, right?
Yeah.
Is it
yeah.
clear?
Yeah.
But your question is what happens in this, between this yellow and blue one, why we call it metastable? Huh? Okay, yeah, green. And blue.
Different colors.
Is that, Chris, what's your
Sort of,
question?
it's just what is it about those two minima that we take over all these temperature ranges that translates to that blue line? Why do those points form that boundary between the stable and metastable region? Like, I just don't know why. It's like, what are the minima? And like, why is it that the minimum free energy?
It's not the so in this, it's not the minimum. If we zoom in, you will see it's not the minimum. So let me make this point clear. It's not the minimum first. So if you zoom in, this particular, I'm going to make it super big.
Okay.
So this is going to be the minimum, right?
Uh-huh.
But in the case we draw, it's not the minimum, it's the intersect of here. So it's going to be intercept here.
Okay, so it's just the tangents.
It's a tangents of that.
Okay, I probably don't want to get into why that is too much.
No, today we don't have enough time, but next class I'll help you guys to understand why we call this metastable, given the time. Okay? But is it, for at least for now, I want you guys to understand between two phases and one phase, why we absolutely want to form two phases in this case. Okay? And next class we will restart and continue to talk about spinodal, why the region between spinodal and binodal we call it metastable. It's actually relatively easy to understand. So any question?
So we have our next test.
Oh, it's quite far away, at least 2 weeks from now.
Okay,
Sounds good.
just checking.
We have, so let me rephrase. We probably need one class to wrap up this part. Where we haven't talked about is how do we get this critical temperature, which is at which temperature your system is always mixed. Okay, we will talk about this, and all these are under the definition of the polymer phase, solvent phase. And again, like we did it in the Flory-Hagen series, we're going to do one thing is convert this to be a polymer solvent case, which we will likely take another class, so at least 2 class. Then there's going to be one more class to explain to you what is chi is, because we haven't really discussed in more detail what is chi really are. And I want to spend one class to explain to you the physical meaning of what chi. And there's fourth class, which is the last part of this. We will talk about osmotic pressure and how does this ties in the solution theory. So I think going to be 4 class and probably 5, because we're going to have a class to review the homeworks. So in about 3 weeks we will have a final test. Not final test, but intermediate test for this class. So expect it to be November 10th, around before the Thanksgiving Day.
Okay.
Definitely before Thanksgiving, okay? That time frame. I'll reach out to you guys about 1 week or 2 before, let you guys know when the final date will be. Okay, clear? Okay, then I'll see everyone next week.
So spinodal is the inflection point, and then the binodal is where they intercept.
Yeah.
Yeah?
Yeah.
Okay.
It's a tangent point between these two.
Okay.
Not the lowest tangent point. I guess Chris asked a very good question, because if you look at far away, it might be think like
Yeah. I just kept thinking minimum, but yeah.
no, it's not.
And he
Yeah.
said it